In late 2025, astronomers observed a rare object passing through the inner solar system, an interstellar comet known as 3I Atlas. New color images from the Gemini North Telescope revealed a faint green glow surrounding the comet, providing fresh evidence about how material formed around another star behaves when exposed to the sun. These observations add to a growing body of data collected by multiple major observatories, helping scientists refine their understanding of interstellar objects and their physical properties. In this video, we will examine what was observed, why it matters scientifically, and what it may tell us about future discoveries of interstellar visitors. Let's get started. The 3I Atlas was first identified on July 1, 2025, by the Atlas survey as it entered the inner solar system at unusually high speed. Its trajectory was immediately recognized as hyperbolic, placing it among the rare class of objects that originate beyond the sun's gravitational influence. This classification made it only the third confirmed interstellar object ever observed, following Oumuamua in 2017 and Tué Borisov in 2019. Once its nature was confirmed, astronomers quickly began a coordinated observing campaign. Both ground-based and space-based telescopes tracked the comet as it moved closer to the sun. The timing of these observations was critical. As comets approach perihelion, solar heating drives the release of gases and dust, making their internal composition and physical structure observable. The 3I Atlas passed through solar conjunction on October 21st and reached perihelion on October 29th. During this period, its appearance changed noticeably. Earlier images taken from the southern hemisphere showed the comet with a muted reddish tone. However, new observations from the Gemini North Telescope in Hawaii, using a combination of optical filters, revealed a faint green glow surrounding the comet's coma. This color shift reflects real physical processes. As the comet warmed, different volatile materials began to sublimate from its nucleus. The green emission detected in the Gemini North images is produced by diatomic carbon, a reactive molecule that fluoresces when excited by ultraviolet sunlight. Its appearance indicates that fresh material became exposed as heating progressed, revealing layers that had remained inactive earlier in the comet's passage. The composite Gemini images also show background stars and galaxies stretched into multicolored streaks. This effect is caused by the comet's rapid motion relative to distant objects and serves as a visual reminder of how dynamically extreme interstellar objects can be. These observations were collected as part of the Shadow the Scientist program, which allows members of the public to participate in real astronomical observations. While the outreach component is notable, the data itself contributes directly to professional research and complements observations from other major facilities. Together, these measurements provide a detailed snapshot of how an interstellar comet responds to its first close encounter with a star like the Sun. The scientific importance of 3I Atlas lies in its ability to act as a physical sample of material formed in another planetary system. Unlike indirect observations of exoplanets or circumstellar disks, interstellar comets offer a rare opportunity to study solid matter that originated around a different star. The detection of diatomic carbon is particularly informative. While this molecule is commonly seen in comets, its emergence at this stage of the comet's evolution suggests a layered internal structure. As solar heat penetrates the nucleus, different compounds are released at different times, revealing how volatiles are distributed within the body. Spectroscopic observations from instruments including the James Webb Space Telescope indicate that the coma of 3I Atlas contains carbon-rich gases such as carbon monoxide and carbon dioxide. These compounds are consistent with formation in a cold, distant region of its original planetary system, where volatile ices could remain stable for extremely long periods. Another defining characteristic of 3I Atlas is its velocity. It is traveling significantly faster than previous interstellar visitors, implying that it was ejected from its home system through a high-energy process. Gravitational interactions with massive planets or close stellar encounters, are considered the most likely mechanisms capable of accelerating an object to such speeds. Observations have also revealed subtle variations in brightness and coma structure. These changes suggest uneven outgassing, possibly driven by localized jets or an irregularly shaped nucleus. In some images, the dust tail shows geometry that differs from what is typically seen in long-period solar system comets, indicating that familiar cometary processes may operate differently under interstellar conditions. Despite occasional speculation in popular media, the physical and chemical behavior of 3I Atlas is well explained by known natural processes. Its emissions, dynamics, and morphology are consistent with established cometary physics, even if the object itself formed in an unfamiliar environment. From a theoretical perspective, each new data point from 3I Atlas helps refine models of planetary system formation. The presence of volatile-rich material supports the idea that many planetary systems produce and eject icy bodies, contributing to a population of interstellar debris moving quietly through the galaxy. The study of 3I Atlas has implications that extend beyond this single object. Its detection reinforces the idea that interstellar objects may be more common than once assumed. With 3 confirmed detections now recorded, astronomers anticipate that upcoming survey facilities, particularly the Vera C. Rubin Observatory, will identify many more such visitors. This shift would allow scientists to move from isolated case studies to comparative analysis, examining trends in composition, size, and behavior across multiple interstellar objects. Such a dataset would significantly improve understanding of how planetary systems exchange material over time. 3I Atlas also provides evidence that volatile compounds can survive interstellar travel for immense durations. Despite prolonged exposure to cosmic radiation and extreme cold, the comet retained reactive materials that became active once heated by the sun. This finding has implications for the long-term preservation of organic and volatile compounds in space. As the comet moves away from the sun, continued monitoring will focus on how its activity declines. The post-perihelion phase offers insight into how quickly volatiles are exhausted and how the surface responds to thermal stress. Comparing this behavior with that of long-period comets from the solar system will help determine whether interstellar comets follow similar evolutionary paths. The passage of 3I Atlas has also renewed interest in rapid response space missions. While no spacecraft could intercept this object in time, its discovery strengthens arguments for mission concepts designed to rendezvous with future interstellar visitors. Direct sampling would provide unprecedented insight into material formed around other stars. On a broader scale, interstellar objects demonstrate that planetary systems are not isolated. Over cosmic timescales, stars exchange material through ejected debris, creating a subtle but persistent connection across the galaxy. Interstellar comets represent tangible evidence of this process. Each detection improves observational readiness and deepens understanding of how common such exchanges may be. Interstellar Comet 3I Atlas has given scientists a rare look at material formed around another star. Its green glow and evolving activity reveal how interstellar objects respond when exposed to our sun. As more such visitors are discovered, they will continue reshaping our understanding of planetary systems beyond our own.